Apparently I can. Okay, I think it is recording. Thank you. I don't know. I may or may not be able to retrieve the recording later because it's a different device, but good point. Thank you. I think, wait, does it say on your end that we're recording now? Like, do you have any indication that we are now recording?
Yes.
Yes. Okay. So thank you for, and maybe remind me later. I'll have to put these two recordings together somehow, but good point. Thank you. All right, let me go back. So, I mean, literally this is embarrassing. Okay. Okay, just to be, again, as clear as I can be, we now have a conjecture. It doesn't prove that we're right. We have not proven that we're right, but we have completed the conjecture. So we have to test it in the last 10 minutes of class. That's what we're going to do, is test this thing and make sure it's right. But and by when we do that, I'll remind you what I mean by right or whatever. But what I know right now, I'm saying we have a complete conjecture. We have something ready to test because it is complete, meaning it has the right form. It is a function of t that returns x, like x is the dependent variable, t is the independent variable. That's correct. And then everything else, is a constant. That's very important. Like, we don't have too many variables or something. We have exactly two. These two things are constants. They have appropriate units. And so this whole thing checks out in terms of units. It checks out in terms of limiting cases. That is, it returns the correct values for in the extreme scenarios that we can already know, from our intuition. And I might add one final thing. It has exactly two arbitrary constants, two constants that is unspecified but unvarying numbers. And the fact that it has two actually turns out to be a really, really good sign and not a coincidence, because what we have here is a second order differential equation, right? We have something whose second derivative is supposed to equal something. And remember, what we're trying to do is work those derivatives backwards and get a function. In the simplest scenarios, when you work derivatives backwards, you do something called integration. And you all know that when you do indefinite integration, right, every indefinite integral spits out an arbitrary constant, right? I mean, again, a slight sidebar here, but if you do the indefinite integral of the x squared dx or something, what do you get? You get x cubed over 3 plus c, right? Whenever you do an indefinite integral, it spits out a constant. So if we, in effect here, are trying to find a function toward which we would have had to integrate twice to get it, it actually stands to reason that we've got two constants here. That's actually a real thing. The number of constants we have should correspond to the order of the differential equation. But anyway, so we know we've got something now ready to test. What does it mean to test it? What does it mean to find out whether it's right or wrong? Well, that goes back to the question of what is it we're looking for? And this is going to be the last thing we do, obviously, at the time. Okay, perfectly, 7 minutes. The question is, if we want to find out whether this is right or wrong, what we were looking for some function such that the derivative with respect to time of the derivative with respect to time of that function yielded the function itself times some constant times a negative sign, right? That's what Hooke's law is saying. That the differential equation is saying we're looking for a the differential equation says d2x dt squared equals negative x. It's saying we are looking for some kind of x, which when you differentiate it twice with respect to time, you get back x itself, but times some set of constants times a negative sign, right? So the question is that the case for our x that we are conjecturing here? So how can we test that? Well, what we need to do is differentiate our x here twice and see if what we get back, and please do write this down if you can. I'm going to say this again. What we need to do here is differentiate our x twice, our proposed x, our conjectured x. We have to differentiate it twice and see if indeed what we get is x itself times some kind of constant times a negative sign. Like if we do, then we win. Then well, I guess I will. I guess I did just write it down. Okay, I'm going to turn the page quick. I know we have like 2 minutes. So we're going to literally take derivatives now and see what happens. And I'm going to do it quick. And you might recognize these derivatives from math methods. Homework 2, that's the whole point of homework 2. It's looking at this whole thing from a different angle. But here we go. And I do have to do it quickly. So we're testing x equals x naught. So we take the first derivative of x with respect to t. We do that, well, we get the derivative of cosine is negative sine, but then I'm doing this quickly and I'll go over this again next time, I apologize, but the derivative of cosine is negative sine, but then there's chain rule because it's cosine of a function times t, it's cosine of omega times t. So by chain rule, we have to take the derivative out, the omega out, and we get that. That's the first derivative. Then we take, I know I said that kind of fast, but it's a trigonometric derivative with chain rule. Then we do it again. The derivative of sine is not negative cosine, but just cosine itself. So the negative sign stays, but the omega comes out again. So we get negative x naught omega squared. I'm looking at the time. Okay. Cosine omega t. Now let me just rearrange that a little bit to make it easier to look at. I mean, multiplication is commutative, right? So I can say it like this. Oh, and would you look at that? Apparently, if I'm careful, if I notice what I'm doing, apparently, when we took two derivatives, we did get back x, right? Remember, x is x naught cosine omega t. So when we took two derivatives, we did get back x times some kind of constant times a negative sign. Now, what's this constant? Well, this is really a constant times a constant, omega squared. But a constant means just some number. A number times a number is a number, right? So this is a constant. Now what was it originally supposed to be? according to our original differential equation, it was supposed to be a constant divided by a constant, known as K over M. A constant divided by a constant is just a constant. A constant times a constant is just a constant. Are these the same? Well, if this works, then they are. Or if they are, then this works. In other words, what I'm saying is this is the final conclusion. We just actually, in effect, we just learned two things at once. We just learned one, our proposed solution does work. X naught times cosine omega t does satisfy the differential equation. It is the position time function for a mass on an oscillating spring, as long as, or if and only if, and this is the last thing I'm writing, and I'm sorry to keep you, but this is so in other words, x equals x naught cosine omega t is a solution to this, to Hooke's law, as long as, or if and only if, omega squared means the same thing as K over M. In other words, if omega squared is one kind of name for a constant for which another different name is K over M, and by the way, check the units, they totally work, the units would be the same. In other words, i.e., what we just learned is that this thing, that if you want to know where something is in time, if it's a mass on a spring, well, what you realize is it's going to co-sinusoidally go back and forth, and you can totally predict its motion at any time as long as you know that the rate of cosinusoidal oscillation that it'll undergo is precisely the square root of the spring stiffness divided by the mass. In other words, we just learned two things at once. Yes, the cosine solution is the solution. And what was that omega angular frequency rate thing? We just learned that the angular frequency, the rate at which this thing will oscillate, fully depends on nothing but the strength of the spring and the heaviness of the mass, the parameters of the system. That's it for today. I mean, but that's the conclusion. So that's the answer. Oh, and if you want the answer to the homework, then you literally plug in the number 1 for T there, and plug in 200 for K, plug in 0.3 kilograms for M, plug them all, take the cosine, make sure you're in radians, and whatever your calculator spits out, that's the answer for X for the very final question of homework, which I believe is 0.116 meters. I believe you can check. But that's it. Sorry to go over. Oh, I think I went over one, but that's it. That's the answer. I'll pause I will try to put the two recordings together. I'm so sorry about the weirdness. Sorry to everybody in the universe, all 10K of you. I will hang out for a second if there's any questions, but other than that, goodbye. And I can't see the goodbyes, or I can't see you. I'm so sorry, but I'll hang out for a second if there's any questions.
Take care, Professor.
Take care. Thank you. Take care. Maybe I can't see. If I go like this. Oh, bye. Oh, I do see the chat. Okay, bye. If there's questions, I can see it, I think. Chat. Okay. You all good? Oh, you good, Jennifer? Are you there? Are you there? Anybody look? You good? Okay, I'm gonna go. Thank you.